Now for the final part of this question, you're asked to identify the fuse that is most suitable for the kettle. Now the normal current that should be flowing through the heating element is 9 amps. So if you were to choose 1 amp, 3 amps or 7 amps, then even with the normal current that should be running in the appliance, the fuse will blow. So what we have to choose is always the next fuse up. So what we're going to go for is the 13 amp fuse. Okay. So we always choose the fuse that's closest in value to the actual current, but it must be higher to stop the fuse blowing or melting as soon as it's placed in the circuit. Right, question 8. We've got a train travelling from station A to station B, and you're going to be working at the speed of the train. And the first thing is just to state the equation. So our equation is average speed is equal to distance moved divided by time taken. 1 mark for that. Then you've got to calculate the average speed and give its unit. Okay, so we've got our speed equals distance over time. You're not going to get a mark for that equation because you've already given it here. The distance travelled is 9 kilometers and done in 15 minutes. Now when it comes to giving your answer, there's a range of units you could use. I'm going to choose to put it in kilometers per hour, so that would be 9 kilometers divided by 0.25 hours. Now that gives me an average speed of 36 kilometers per hour. Okay, I could have used any units if I'd wanted. I could have done it in meters per second as well. In that case I would be doing 9,000 meters divided by 15 times 60 for seconds, which is 900 seconds, and then that will give me 10 meters per second. So either of those is fine. Now the maximum speed of the train must be higher than this value we've calculated. The reasons for that are, well, firstly, the train speed is not going to be constant for the entire 15 minutes. There's going to be some fluctuations in the speed. So at some points, for example, when the train is leaving the station, the train's going to be going much slower than the average speed. In fact, it may even be stationary to begin with. And because it's going lower than the average speed at some points, it must also be going faster than the average speed at other points. So it's going to have a maximum speed which is higher. So the train continues along the track from station B to station C, and the graph below is a velocity time graph showing how the velocity changes with time for this part of the journey. Now you're being asked to calculate the acceleration of the train during the first 100 seconds, so just in this period that I've labelled there. Now acceleration can be worked out in two ways. Either we can use the equation, which is acceleration is change in velocity over time, okay, where v is the final velocity and u is the initial velocity, or the acceleration is the gradient of a velocity time graph. Now both calculations are essentially the same thing. Okay, so I'm going to use the equation this way. What's the change in velocity? Well, the train has gone from 0 to 30 meters per second, so therefore the change in velocity is 30, and it's happened in 100 seconds. So if we do 30 divided by 100, then we get 0.3, and the units meters per second squared. For the next question, it says use the graph to calculate the distance in meters between stations B and C. So let's go back up to the graph. Now you can always work out distance from a velocity time graph because it's always the area under the graph. So I've split the area under the graph into 3 different areas, 2 triangles and a rectangle, and we'll call them A, B and C. Now what we need to do is work out the area of each and then add them all together. So this is a triangle, so the area can be found base times height over 2. A rectangle, base times height, and base times height over 2 again for this. And we're going to add the results of each of those. So base times height for triangle A, well, we've got 100 times 30 divided by 2, and we're going to add that to 100 times 30. For rectangle B, and we're going to add that to 100 times 30 divided by 2 for the final triangle. And if we add those all together, then what we're getting is 6,000 meters. Okay, because we get 1,500 meters for C, 3,000 meters for B, and 1,500 meters for A. Okay, question 9. So we've got a builder who's working on a new house, and he carries a concrete block from the ground up to the top of the scaffolding. And you're being asked to state the equation linking GPE, mass, G, and height. Now, I would always use the symbols that they give to you. I'm just going to do it shorthand here. But gravitational potential energy is equal to mass times gravitational field strength, acceleration due to gravity, and times height. And then we've got to calculate the GPE. So using the same equation, all we've got to do is plug the numbers in. Well, it's 18 kilograms. G we're going to take as 10, which is always given to you on the front of the paper, and H as 5. And that comes out as 900 joules. Then what is the link between the gravitational potential energy gained by the concrete block and the work done by the builder to lift it? Well, if the builder puts in 900 joules of work lifting it up, then it will gain 900 joules of gravitational potential energy. So all we need to say for this is that they are the same or equal. However much work is done against gravity is the gain in gravitational potential energy. Okay, for part B, the builder fits a layer of insulating material in the roof of the house. And basically we've got some aluminium foil with some fibres in between, and there's air trapped between each of the fibres. Now you've got to explain how this insulating material reduces the amount of heat loss through the roof by each of the heat transfer mechanisms: conduction, convection, and radiation. And I think the easiest way for me to go through this is basically just to look at the mark scheme that was given for this paper, because what they say straight away is that there's up to 5 marks in all, for which 2 for each of the mechanisms. So really we're looking to try and write 2 significant points about each, and we'll get 2 marks for 2 of them and 1 for one of the other. So starting with conduction, what does the mark scheme think are the most important? Well, you're going to say that air is a poor conductor, or it's an insulator. Add to that why. The main reason really is the air molecules are far apart. One thing we should know about conduction is that one of the main ways in which conduction happens is that particles vibrate and pass kinetic energies from vibrations onto their neighbouring particles. If there are no neighbouring particles, then obviously that's going to hamper conduction. So they've also said the fibres themselves are insulating for one of the marks. So anything from there up to 2 marks. When it comes to convection, the essential point we're after is that it reduces convection currents. Okay, the reason for that being that the kind of pockets of air are unable to rise all the way up through the insulation, because they get to a fibre and won't go any further. They've accepted a mark for the air or gas cannot move. And then we've got radiation. How do we stop that? Well, we're going to say that the radiation is reflected. It's going to be our key point here, okay, because the aluminium foil is a shiny surface. And those would have been the 5 things I would have written down there to try and get the 5 marks. Right, this question is about electricity, and we're looking at a thermistor and seeing how its resistance changes with temperature. Firstly, you've got to label the thermistor, which hopefully is pretty obviously this. And then you've got to add to diagram to show how the voltmeter should be connected. Well, he's looking for how the resistance of the thermistor changes. So the voltmeter has got to be linked to the thermistor. And voltmeters are always placed in parallel with the component you're measuring the voltage across. So the student varies the temperature of the thermistor and obtains the following current readings. They want you to state an equation that links voltage, current and resistance, while voltage is current times resistance, from this triangle here, and therefore we would also accept R is V over I, or I is V over R. And then we're going to use that to calculate the resistance of the thermistor. So we want resistance, so we're going to use this form. The voltage is 12 volts. Now the current depends on the temperature. They've told us 20 degrees Celsius. So 20 degrees Celsius, the current is 2 milliamps. Now 2 milliamps, okay, is not the same as 2 amps. So we need to make sure that we've divided that by 1,000. Okay, and that's because there are 1,000 milliamps in an amp, in the same way that there's 1,000 millimeters in a meter. And if we do the maths there, and we get 6,000 ohms as the resistance of the thermistor. And now we have to use the results from the table opposite to plot a graph of current against temperature. Okay, so first thing we're going to do is label the axes, and we're going to make sure that our labels have got units, the correct units being degrees Celsius and milliamps. We're then going to add a suitable scale, so the temperature needs to go up to 100 degrees, so I've gone up in 20s on my scale, and the current needs to go up to 30 milliamps, so I've gone up in 5. You then need to plot your points. I think it's better to use crosses rather than dots, because there's a definite centre to them. Make sure they're big enough that you can see them reasonably clearly, and then we need a best fit line. Now best fit can be straight or curved. In this case it's pretty clearly curved, so we don't have to go through all the points. We're going to do a trend line which follows the general trend and should be as smooth as possible. And once we've drawn the graph, we're asked to use it to describe how the current in the thermistor changes as the temperature increases. Now the first thing, the most obvious thing, is that as the temperature increases, the current increases too. Okay. Now what we've got here is not a straight line though, so we don't have a linear relationship between temperature. And what you should be able to see is that the line is steeper at higher temperatures, and the way we can describe that is we can say at higher temperatures any increase in temperature of 10 degrees, or in fact any unit of temperature of 1 degree even, will cause a bigger increase in current. You can see that down here on the graph, an increase in temperature of say 20 degrees here causes an increase in current of around about 3 milliamps, sorry. While here, if I increase the temperature by 20 degrees, I get much more than 3 milliamps extra current. I get over 10 milliamps. Now the student has drawn their own conclusion from this experiment, and they've said as the temperature increases, the resistance of the thermistor also increases, and we've got to evaluate this. Well, first of all, is it correct or not? Okay, as the temperature increases, does the resistance increase? Well, looking back at the graph, okay, resistance is not on our graph, so what we do know is that as the temperature increases, the current increases. But what does that tell me about the resistance? Well, resistance and current are inversely proportional here, so the higher the resistance, the lower the current. So the student cannot be correct.